Okay, so if you remember, we've been working with a surface similar to this, and we've mapped stuff onto that surface. So when we not last week, the week before, the one that we did with the bamboo, we used a 2D pattern to map onto the 3D surface. Yeah. Last week, do you remember what we did to project? Well, we projected curves onto the surface instead of mapping them. Okay, so the process for this week, and this is why I've asked people like Blair to use this geometry, is that we're just using planes to section through, and the key reason we're doing that is the outcome has to be planar. Okay, so if I were to start putting glass panels on this, we need planar output. The holes that we produced with the bamboo, they could have been non-planar, right? Like we weren't forcing that to do anything in terms of its planarity. So one thing that we can use in this case is the geometry. If we slice it in a certain direction, it's guaranteed to be planar, the panels. And so if you take a hyperbolic paraboloid and you slice it in the direction of the first parabola, and then like if we look at that as a section through there and we slice it through this way, like so, looking at it from the side, these elements end up becoming planar. Okay, so this isn't something that you can just do on geometry, like any geometry. It's something that we have to do this specific way for this specific geometry. So a lot of you are going to end up with the exact same outcome. Okay, that it's just how it is. Cool. So, do you all have this surface in the rotation where it is forced to be pointing like either in the X or Y? No? Huh? Can we do it again? Oh, well, we can. I'll do it. Like so what we'll do is we'll assume we need this particular module. Oh, fuck. Airplane mode. Hello. Okay, it's still recording. Good. Okay, so, geez, already running out of time. Okay, so what we want is our module. So this is going to be the module that you've been working on. It seems like every week someone's not using that. So hopefully we're using that module now. Now I'm just rotating this now to just put it into a random rotation. In no way do you need to rotate this. This is just an example. So that there's a random rotation. Let's go like so. Okay, so that's been randomly rotated. So fortunately, this surface is still maintained its topology. So without actually knowing anything about its geometry, we can probably quite easily get its information about if we untrim and get bifocals. So bifocals. So first things first, ignore the divide surface. We want to untrim it. like so. We'll plug that into a divide surface. So that'll show us the points divided in U and V. We'll put in a slider and set that to a maximum of 3 and 0, 0 to 3. And so what that'll let us do is set those values U to 1 and V to 2. It might be the opposite. The key thing is we want a point here on the far right in the middle, and here on the far left in the middle. Okay, so what that should do is just give us a quick little branch structure of 3 points in 2 branches. So this first 3 points will be these guys on the left. And the second branch should be the points, these 3 points on the right. Okay, 2 branches representing each column of points. Cool? So the midpoint, this point here in the middle, should be the second point in each of these lists. So if I grab the list list item, and set that index to pick up 1, that will give me the middle point of that surface. Like so, there to there. So we should now be able to use these 2 points to reorient this thing so that it's facing the direction that we want it to. So it's at this point that we want to flatten, giving us the 2 points in a list. We'll then go to a list item. The only reason we're doing this is because we just need to split those two. We just need to split those two. Well, actually, let's do this a different way. Now, after we've flattened, if we create a polyline, that'll give us that line that it'll visually represent the line that we want. Fortunately, that means we've used a list structure to make the polyline. We break that polyline into its endpoints, giving us the start and end. It's just all that's doing is it's splitting these 2 points into 2 separate lists, a start and end. We then create a vector 2 point between those 2. So that's just giving us a direction and a start point for the vector, which is basically all we need to now produce the rotation or an orient to get us to the flat plane. So what's the easiest way to do this? If I grab an XY plane and I plug that into the start point, and then I orient that plane, align that plane in the direction of the vector. So the vector 2 point will go into the direction. And then I transform the surface by the angle output. So if I grab a rotate, I just need to rotate on this XY plane. So that's the plane. The angle is the A coming out of this, and the geometry will be the G. So that's the module that you're working on. And so in my case, it's the one that I've rotated, but in your case, it could be, it's just your module. So plug that in, and then we just need to set the A value to be, I believe, -X. And that will rotate your surface into an orthogonal plane. Cool. We need it to do that. This is a really important step because if we don't do this, then the rest of the stuff won't work.
What's the expression?
The expression is negative x. I'll Cool. Okay, so it's at this point that we need to start we're going to start slicing our model up. So we don't need, we can just hide all of this information, and we're just going to work with our rotated model. And the key point is that it's oriented in the right fashion. So we are going to generate some planes to cut it. We're going to use the same methods that we did with the waffle system. So we are going to measure, this should all be familiar with waffling. Was the waffling video the one that got broken into bits? Like it wasn't really, yeah, okay. Well, hopefully this one's being recorded. Yeah. Okay, so what we're going to do is we're going to work on the waffle system in a similar fashion. So we're going to get the bounding box of our surface. That'll give us the domains. If we break that down into, if we deconstruct the box, that'll give us a domain in X and Y. So with that, we can divide a range up for the X and Y. We're going to do this quickly. So we're going to use a range. We're going to use a range for X and a range for Y. And the value that goes into these two ranges will be, an integer, and we'll say, it can be up to like 6 or 10. And this is going to produce points. So the X domain that gets divided into a range is going to control points in the X direction, and the domain that is divided from Y is going to produce points in the Y direction. A key factor of this is we don't actually want it to generate a point on the very ends because it's going to slice through our model at the wrong position. So we will use a cull index, and the indexes that we want to cull are the start and end. So the start and end is 0 and -1. So that's now culled those ends, and the points that are being produced in the X direction need a YZ plane, and I'll make my plane a little bit bigger so that you can see it, because at the moment it's set to 0. So there it's set to 50, and XZ in the Y direction, so that will produce planes running in the opposite direction. So at this point that we want to generate sliced lines through our section, and if anything, we don't actually, we probably want to work on the extended surface, like the untrimmed one. So we want to effectively untrim the surface again once it's been rotated, like so. And we're going to use the YZ planes to slice through that with an intersect. So we're using B-rep geometry with planes to create those slices. And so we can see there that the slices through that untrimmed geometry. Pardon? The thing that we rotated. Cool. Okay. So if I were to just analyze these, they're definitely parabolas, because the way that we made our hyperbolic parabola weeks and weeks ago, it might have even been like a month and a half ago. These should be planar vertically as parabolas, and but the thing is, if I were to just start like cutting, if I were to loft these together and unwrap it, what type of geometry is this currently representing in 3D? Like a non-planar geometry, one that is still double curved, right? Like we need to start making these lines straight for it to start being planar. Okay, so the idea is that if we have these planes cutting through our geometry as well, if I slice these planes with my curves that I've generated, no, actually let's do this. Let's also trim the surface in the other direction. Oh, I just watched someone pick their nose and eat it. Okay, so this is giving us effectively two sets of curves that are going, they're creating a grid, okay? And what we need to do now is truncate our lines to effectively panelize this form. So when we truncate this, when we start making these straight lines, just have a guess, where do you think the straight line should go from and to? If you were to just quickly draw a straight line right now, one straight line that would be in this system, can you instruct me where to draw a straight line from and to? Anyone? No one? From an intersection of two of the curves to another intersection of two of the curves? That's where I draw a straight line from and to? Yeah? Yeah, it's not a hard question. Like, it's not a trick question, more so. Like, it's pretty straightforward, right? The point is, what we need to do is work out where those points are between those two curves. Okay? So we've got two curved lists, and we can see these are all branched. So what we'll likely have to do is flatten them, just to avoid any branching issues for the script. And we need to find the intersection between those two curves. So I think this is the first time that we've used a curve-curve intersection. No? We've used it before? Yep, okay, excellent. So we can, if we plug our lists of curves in, we're getting our, that same issue that we normally get with when you put two lists together. Without sort of like sounding like a broken record, because I repeated this last week, and I also spoke about it the week before. if I wanted all the points to appear, I would effectively have to graft one of the lists. Yeah? Does that make sense? Because we're effectively we want to cross-reference one list with the other to generate all the points. So if I then graft the first list that goes in, that's going to produce a grid of points. Okay? How did Christina do this? Yeah, but that's not going to do the full thing, is it? Okay. So we've got a list of these points, guys. So if I were to but they're currently branched in a fashion that like how many points are in each branch? How many points are in each branch? 1, right? And what's the, if I simplify the branch, there are two numbers in the branch address. So what that means is these guys currently have created a branch per point, but what it looks like is there's a greater structure where there's actually 3 points in each greater branch. Okay, so we've spoken about flattening, and we've spoken about grafting. So what does flatten do to a tree structure? Anyone? It destroys the tree structure and effectively puts all the points in a single list with no branches. Okay? And what does graft do to a tree structure? Huh? It creates a branch, an individual branch for every object in the tree. Okay? So we haven't spoken about another function, which is it's called trim tree, and what that does is it effectively destroys one of the branches, but it doesn't flatten the whole tree. It just flattens down one level or 2 levels. You can tell it how many. Okay? So in this circumstance, once we've simplified, so just to make sure that it's simplified, we're going to put in the simplify tree just to guarantee that everyone's listening to me. Then if we put in this thing here, trim tree, what that does, it's either trim, but you could either use trim tree or shift paths. In this case, we want to shift the path of the tree by -1, or if we want to trim the tree, we want to trim 1 level off. Okay, so they work very similarly, but if we just use trim tree for now, if I plug that in, we can see that it will take these branches and destroy the right one, the very first right one. Therefore, these 3 elements that were grafted then compress and flatten by 1 branch into the branch 0, then the next 3 into branch 1, the next 3 into branch 2, and the next 3 into branch 3. Does that make sense? Okay. So what that means is we can now use those to produce the polylines, but it's not doing the full extent that we need either, right? Because what we need is this to actually go the full extent, yeah? And we're missing the endpoints, yeah? So we can go one of 2 ways. Remember how we trimmed, remember how we got rid of the start and end plane? We can either bring them back, but if that plane misses the curve by even the smidgest, like tiniest little smidge of millimeters, it's not going to produce a point. So we can either bring those planes back and extend our lines so that they go through those planes, or we can get the endpoints of the line. I think we should do the extend system because it would require the least amount of coding. Okay? So what that means is, see these color indexes? We're going to get rid of them. So we're just going to bypass those. Oops. I actually think that worked. We don't even have to extend. And just to make sure that it's working, once we produce these B-reps, the B-rep plane intersections, we're just going to put in an extension to these lines. So we'll grab the extend component and we'll set that to, let's say, 20 mil. Yeah.
Why is it that when you click on the wires, it puts this little thing in it?
If you double click,
Yeah, what's that for?
it's a relay. It's just to help organize your wires. So like, for example, if I like, it also lets you turn off the connection between the two without turning off the component. And you can, I believe you can name it. So, cool cable. Oops. So it helps you effectively label and organize your script. And then if you, let's say you've got a whole bunch of wires connected to a flattened tree and you want to, like, let's say we do this. Oops. Right, let's say we do that, right? And it's a mess. Like, you want to get rid of, like, this one specific one, but when you go, okay, I want to disconnect one, right, like it's a bit hard to work out which one you want. You could sort of say, okay, let's double click this wire. It's not going to work now. Why isn't it working? Maybe. Wow, it's buggy. It's only working for, oh, there we go. Okay, so let's say we just want to get rid of this wire. We can say, okay, this is less, we'll just say 1, right? Then when we go to disconnect, it's labeled as 1. Like you can actually see, like the wire has a name and we can see what it is. So it's just to help organize things. Those of you who are copying me, okay, so we have our extend and we need that to be on both of these. And really that's just there to help us guarantee that if there's any like non-plane intersections there, we're avoiding them. And what that should then also do is that should have fixed up our polyline. So if I now show the polyline, Christina's always changing the bloody display. So that means if I show this polyline, I should be getting my truncated curves that are cool. Okay, So this should apply the exact same way in the opposite direction. So if I copy and paste that, and instead plug our second flattened tree into the graph tree and our initial flattened tree into the B, we should be producing like a nice little point grid of lines, which we're going to eventually use to make frames. Okay? Right. So it's at this point that I need to sort of give you a warning. I would continue doing this process in a very sensible fashion, using B-wraps and surfaces. I would not use meshes in this case, right? But this particular tutorial is about helping you guys get your head around meshes, yeah? So it's really from this point that we're going to start using a mesh when we really don't need to. Cool? Does everyone forgotten your name? Yeah. Abigail. Sorry for forgetting your name. Could you please give me a brief definition of what a mesh is? Yeah. Were you in the lecture last week?
No.
Weren't you?
Oh, am I? No.
You weren't in the lecture?
No.
Who was in the lecture last week? One person was in the lecture last week. Curtis, can you give me a definition of a mesh?
Polygons.
Okay, I'm hearing something that a mesh contains.
The surfaces.
Keep going.
I was gonna say well, I guess a mesh, you use it in comparison with video games.
Yes.
And in video games, it's when you see something, it's a surface, right? It's a mesh.
Okay, so right now we're gonna slow down with the syntax, right, and the words. A surface in this particular room means a mathematical NURBS geometry that is made up of curves, and it can be it's always four-sided. Surfaces are always four-sided, right? So we're not going to say surface now. We're going to use another word, okay? So is there like a shell, like it's a geometry, like what? But either way, good attempt, but it doesn't necessarily define it. Do you want me to have a go? Okay. A mesh is a cloud of points in 3D space. Points and a set of instructions on how to connect them. Okay? So if this is point 0, this is point 1, and this is point 2, then a polygon that goes between them has the instructions connect 0, 1, and 2. So therefore, we get a polygon there. Okay? So this same mesh could have the instructions connect 4, 5, and 6, which would then create a connection here, creating a polygon there. Even though these two objects aren't touching, they are still part of the same mesh. Okay? So this is actually one mesh object, right? And when you watch video games, I'm assuming most of you are aware of League of Legends or Dota or something like that, or what's that new Blizzard game? Overwatch, right? When you see characters that have things flying around them, or when a character throws their gun in the air or does something like so, that thing that's flying around them is probably part of the same mesh. It's not a separate object. And so therefore it's one thing. And so it's the only geometry in Grasshopper where you can have things separate to each other, but part of the same object. Okay? So if I draw a donut with a mesh, I can actually make that one object. Not like if I were to draw that with two curves, how many curves would Grasshopper or Rhino understand that as? 2, right? Even though it's a donut, right? So, second thing, do I have a point that is not connected in my mesh? 3. It's still part of the mesh, okay? So meshes can have points in them that are not used to make geometry. Meshes in Rhino and Grasshopper can be made up of 3-sided or 4-sided polygons. So we can have polygons that look like this, okay? But in Grasshopper, we cannot have a polygon that is 5-sided, 6-sided, 7-sided. But mathematically, meshes can have more than 4 sides, okay? To each polygon, and you may see programs that use more than 5. It's just Grasshopper doesn't use them. Final thing, just note that because of this points and network and a cloud of points and a series of instructions that connect them, that meshes are therefore defined as topologies, okay? So if you have a mesh that has the same topology as another one, then you can therefore do interesting things with those. So for example, animations, so let's pick a Pixar animation. What was their most recent one? Coco. Oh, something everyone's seen, Finding Nemo, right? So if you were to model a mouth, a fish mouth, as a mesh, as a really simple mesh, it might look something like this, right? You can all kind of make out the mouth shape, right? So for someone to make a surprise shape, you just need to change that to something like that. You know, they're eating their little their fish food. Yeah? Yes.
It's not like you kind of have the same look of the character, but just different expressions.
Yes. So what that means is if this is 0.0 and this is 0.0, then you can then basically animate the mesh between the different coordinates without things like spazzing out, right? So this point is linked to that one, and this one is linked to that one, and this one is linked to that one. And so therefore, because you're maintaining the topology, that you just say, take every point and move it to its next point. And we'll see more advanced versions of that in coming semesters, okay? Where we start using physics engines to make geometry, yeah? But we'll just as long as you understand that. The last thing, because meshes are topologies, we can use them to represent other things other than geometry. So you could use a mesh to represent social network connections, right? Because you're friends with someone else, so therefore that is like creating a connection in a mesh. Cool?
Also, why is it called a cloud instead of like a list or a branch?
A cloud of points.
Yeah.
Just, it's my word of describing it, because a cloud clouds are 3D. Think of it as like a cloud of starlings or a cloud of fish, not as a cloud of particles, right?
Yeah.
It's just a cloud of points. Yeah?
Yeah.
One other thing is they don't necessarily have to be physically real. So a lot of you guys might see warnings when you go to 3D print something. It wants it to be watertight. So that's because you need mesh with valence 2, so no edge, every edge has at least one other edge next to it. If you have more than one or less than one, then it's not 3D printable. And that's how it can tell that it's 3D printable. It just checks, does this edge have a neighbor? And then it's done, okay? So that's explaining what meshes are. So if I've got a cloud of points, and the thing is I can use either one of these two polylines are going to be for us to work with later. Right now what we want is, we want to take one of these we want these for later, keep them. We want to keep these for later. Which ones are we keeping for later? Do you know which ones we're keeping for later? No? Okay. These ones we're keeping for later, the ones in the purple. Do not lose them. We're going to ignore them for now. We're going to use them later. The point is, guys, are you listening? We want these trim trees, and we just want one of them. We're going to flatten one, and we're just going to grab the display, and we're going to display these points as a point list. And if I hide everything except for that point list, or actually no, let's not do that. Let's at least leave these polylines on, they're going to help. But the point list, we're going to set the size of that to be a bit bigger so that we can read it. So I'm going to set that to 3. Okay, let's try 10. Okay. So if I've got my cloud of points, my list of points, my, whatever of points, sorry, Arlene, for mixing words up. If we are going to make these out of polygons, these panels, how many sides are our polygons going to have? 4 sides, right? Going to have 4 sides. So if I were to start, if we were to start on the very first polygon, what would its point instructions be?
0, 1, 5, 6.
Okay, that is completely correct. Okay, so we're going to go from 0 to 1. Oh no, it's not completely correct. So if we go from 0 to 1 and then 5 to 6, then what's going to happen? We're going to produce an hourglass, right? So we're going to go 0, 1, 6, 5, right? But we've got one other issue. It's what a direction is that? Clockwise. And which direction do computers want things to be, like if we want to consider them standard? Anti-clockwise. So what we'd want is 0, 5, 6, 1, or maybe 1, 0, 5, 6. Okay? Does that make sense? So we could be absolutely insane, and we could go through and type in each one. So we could go 1, 0, 5, 6. Okay, what's the next one? 2, 1, 6, 7. Okay, that's super dumb. I think we could probably get away with some clever thinking at the moment, but yes. So instead of doing that, there's a few ways that we can go about doing this, okay? First one is we cheat and we'll just loft the polylines, right? So if I've got these polylines here, if I loft them, flatten the loft, break up the, set the loft to be straight, not normal, and then explode it, then we've effectively produced a series of flat panels, right? And if we want to turn them into a mesh, we can do that. So there's this component here, simple mesh. If we plug that in, that effectively produces a bunch of 4-sided meshes for every surface that's there, okay? That's cheating. If you can't follow this next process, just use it, okay? Cool?
Why would you not use the simple?
Because the purpose of this tutorial is to get your head around meshes, okay?
It's using mesh.
Huh?
It's using mesh.
I know it's using mesh, but Christina wants you to construct a mesh, which, to be honest, I've only ever done it once in my career. Is literally gone through and made like a thing that constructs meshes, okay? So it's going to be rare for you guys, but the point is you kind of need to understand it, and this exercise helps you understand it.
So usually we could just do that.
Yep. In no way is, someone in the next semester or, in your career going to be like, oh, you didn't generate numbers that built that mesh topographically perfectly. Because A, we would never use meshes in this case anyway, we'd use surfaces. So just consider that. But in this case, we need to identify a pattern. Can anyone see the pattern? So we need, if we go 0, 1, 6, 5, then we effectively have 0, 1 as a starting set of numbers. Is that a question? And then 5 is 4 plus 1, and 6 is 6 plus 0, right? And then we have 1, 2, 6, 7. So we can see 1 plus 4 is 5, yeah? And we've got 2 plus 4 is what? 6. So there's 6. And 1 plus 6 is 7. So these are following a similar pattern, yeah? Yeah, I know it's simple math, but we can see that there's a pattern there, yeah? So first things first, what we can start to do is create a series of numbers that represent this grid. So everyone's familiar with series? Yeah? And if I start series off at 0 and I set its step value by 1 and its count is, we'll just say it's questionable for now, that's going to give us numbers going from 0 to 9, okay? So what we could do is we could start to say, okay, this series is going to represent these numbers, yeah? So how many numbers do we have in row 1 or row 0? 5, right. Now, is there anywhere in the system that we can count that number? Yeah? So this number here, if I make that 6, oh no, that's the wrong one. If I make this 5, how many numbers do we get in the top row now? Right, so this variable here is actually controlling the grid that we've got, yeah? So what we'll do is we'll just grab that number, and it's probably likely that we need the other one as well. So we need these two sliders. These two sliders are going to actually effectively let us create a mesh. This is completely just an exercise in teaching meshes. I don't even know why we need to print this. It should just be a mesh output. Okay, so this second number is 5. So if we plug that into our count, that's going to produce 5 numbers, 0 to 4, right? But we need that to be 1 more for every row that we produce. So what we're going to do is we're going to set the expression for count to be x plus 1. Okay? Now that is producing a series of numbers from 0 to 5. Cool. now that I've increased the number, we've noticed that the pattern has changed. So it's no longer 1067, yeah? Remember how it was it was going to be 1 plus 5. Now what is it? Sorry, 0, it's 0 plus, it was 0 plus 6, it still is, right? That seems weird. Oh, that's because I put it back. My bad. So if I increase that, now what is it? 0 plus what?
7.
Right, and it's 1 plus 7, okay? So we could either create a little maths function for each polygon, or we could just generate all the numbers and start picking them out as we need to, okay? That's what we'll do. So we've started our series at 0. This is going to be a lot. This is going to take a while. We've started our series at 0, but if I had a series that started at 0, and then 7, and then 14, and then 21, and then 28, and then 35, then I would have 1, 2, 3, 4, 5, 6 series, starting at the correct numbers and going up by 7. Okay? So we know how many these need to step up, right? How much do they need to step up by? 7. And what's this number? That's not the right number. Sorry, it's this number. What's this number? 6. And therefore, 6 plus 1 is 7. Okay? So if we create another series, which we've already, like if we copy this second series, copy it to make a second series, we've already got this expression that goes into the count. We want to take that out, right? We want that to go into the n of it, because n is the step, and we're going to set that to x plus 1, right? So what can we see here? Immediately, we're getting a series that steps up by 7. So we're going from 0, 7, 14, 21. Yeah? This is gonna hurt your brain soon, okay? It's already hurting mine because I'm trying to think about how we're going to move this forward. But how many do we need? How many numbers do we need? 0, 7, 14, 21, 28, 35. We need 6, right? And that is this number here plus 1, okay? So that just goes into our C, and that should produce the exact numbers that we need for the start. Yeah? 0 to 35, 0 to 35. Cool? So we're just creating a number version, an index version of what we're seeing in 3D. Cool? So this is where it gets interesting. If I plug a list of numbers into a series, it's going to produce that many series. So if I plug in these values as starting numbers in this first series, that's going to produce a branched version where we go from 0 to 6, 7 to 13, 14 to 20, 21 to 27, 28 to 34, 35 to 41, okay? It's at this point that I'm just going to reduce the divisions to 3 and 2, okay? Just to avoid mad confusion, especially in my brain. So I'm going to make this 3 and this 2. So we should only really be producing, it's looking a bit like the fish lips, right? So we're just going to work with these numbers. The numbers aren't going up by crazy amounts. You know, it's just 2 and 3, okay? But it's at this point that we need to start breaking this down. So we can see here the first polygon needs to be 1, 0, 3, 4, okay? Which is going to be the first two from the first list, and the first two from the second list, okay? So what we'll do first is we'll get all the first two numbers. Okay? So if anything, we're going to create a system that just gets us the first number. So the first number of the first polygon is 0. Then the first number of the second polygon will be 1. Then the third polygon will have which first number? 3. Okay, so what number did we skip? 2. Okay, then if we just take another process, what will the second number of the first polygon be? What? Okay, let's assume that, let's just go in the other direction. So we're going to go from 0 to 1 for now. We'll sort that out later. So the second number will be 1. Then the second number will be 2. And then the second number will be, right, so which number did we skip here? And we also skipped another number. Right, so if we just look at the first, like if we just consider the first row, like these two polygons, 1, 2, all we've done is we've skipped this number for the first values, and we've skipped this number for the second values. Yeah? Does that make sense? So, have we done something in the past that have we used anything to do that? So if I were to just say, okay, let's get rid of the last number, -1, does that look like it's following the pattern that we need it to? 0, 1, 3, 4, 0, 1, 3. We do the next one. The next one would probably be 4, and this one would be 5. Yeah? So you can see this is already, like, just by removing the last number, we're starting to get a structure that will give us the very first numbers of our polygon. And then the same applies in the opposite direction. So if I get rid of the very first number, that will give us, I'll just structure this like so. That's going to give us the 1, so we can see 1, 2, 4, 5, 1, 2, 4, 5. Yeah? Patterns. Yeah, patterns are fun. Yeah. Okay. So, this is working, right? So, there's just, we've effectively done this part. Just this part. We've kind of fucked up with the next part, which is, if I were to go to the next polygon, what the next value, so 0, 1, what's the next value? No. 0, 1, 4, 3, right? And then if we go 1, 2, it goes 5, 4. Okay, so we can see, we could just use that same system for this, right? If you just get rid of the first value for the second list, 3, so, if you do this process, it'll give you 3 and 4, which is 3 and 4, right? Yeah? But, sorry, 3 and 4. 3, and 4. But how do we get rid of the 1 and the 2? Right? Because we, in a way, is 9 and 10. So here we've said we're going to start a polygon and we're going to go from 9 to 10. But there's no polygon here, yeah? Right, like just consider this. If I start a polygon and I go 0, 1, 4, 3, right? And then I start another polygon, 3, 4, 7, 6. And then next one, 6, 7, 10, 9. Right? 6, 7, 10, 9. 6, 7, 10, 9. There isn't a polygon that goes from 9, 10 downwards, right? So there should actually be, these guys should be removed from the system. They shouldn't be here because they're not starting points of any polygon, okay? This is where we got to start really working with trees, okay? Because what we need to do is get rid of those branches. Those branches shouldn't exist in this list, okay? So this is how we're going to do it. If we grab, now there's probably 3 or 4 different ways of doing this. I wanted to teach you guys the way that I do, which is probably the least complex way because it's the easiest to sort of get your head around, okay? If you go to your parameters tab and grab a param viewer, what that does is it just shows you the branch structure of your tree, okay? If you double click it, it actually shows you a visual representation of the structure of the tree. But we don't need that. The only reason that we're using this particular component is the output of it is actually giving you the branches of the tree. Okay? So can you see the correlating branch structure? So the first branch is 0, 0, 0, 0. And we can see it there, and it's corresponding there. Does that make sense? Jonathan, does that make sense? Can we see branch here? Branch that comes out of the param viewer there is actually an item that's corresponding with the actual branch. So that is just a visual, it's an actual item now, like a text item, that's representing this. Does that make sense to everyone? Okay. It's at this point we can get rid of one of those branches in this list. So let's use this component, col index, again, but we're going to use it on this list. So what we want to do is we want to get rid of this branch, 0030. So if we col that index, that's going to get rid of 0030 from that list, yeah? Okay, now all we have to do is, using this data, we just need to get the branches that we've listed. So we can use this component, I've lost it, tree branch. So what tree branch does is, if you give it the address of the branch and you plug a tree into it, it will give you the branches that you have specified. So in this case, we can see by using it, it has removed the last branch because we've used col index to cull that branch's index. Okay? So we can use this same function, col index, for our second branch. So that produces 0, 1, 1, 2, 3, 4, 4, 5, 6, 7, 7, 8. So now we're no longer dealing with these guys. And just in the same way as we've done here, where, see how, to get rid of the, is the first row of numbers ever going to appear as last points? No. So we're never going to have, whenever we write these, we're never going to write number 1, 0. Are we? No. We're only ever going to write 1, 0, 4, 3. So just as 9, 10, and 11 are never appearing first, we're never going to see 0, 1, and 2 appearing last. So what we can do is also cull the 0 point, the first item from the list, and we're going to copy our 2 tree branches components, and we're going to feed these instructions into those, which will give us zero, 1, 3, 4, right? Which is 0, 1, 3, 4. Yeah? Then 1, 2, 4, 5. 1, 2, 4, 5. Does everyone see that? And then if we just check the last one, 6, 7, 9, 10. 6, 7, 9, 10. 10, 11, 7, 8, 10, 11. 7, 8, 10, 11. Cool? Does that make sense? Does everyone kind of get what we just did? So what we've actually done is we've taken the tree branch address. So for example, if I were to call this row, row 1, and your student, this is row 0, and you're student 0 of row 0. And Blair is student 1 of row 0. And we go 0, 1, 2, 3. Okay? Can the person who is row 2, student 1, put their hand up? Nope. Row 2, student 1. Which row are you? You're row 1. This is row 0. So which row am I talking about? You guys. This row. And student 1, put your hand up. No, you're student 0. So it's this guy.
So that's row 0, and then the first student is 0.
Of course. Every first one is always 0, right? So the thing is, if I were to then say, let's get rid of row 0 and rejig everything, so all the numbers shift, yeah? I want the same addressed student to put their hand up. Does everyone see Arlene's put her hand up? Because we've killed not killed, that's probably the wrong word. We've removed one of the rows, yeah, one of the branches, and now we've got a new, you're now 0, they're now 1, they're now 2. So you have to think of branches as an address, right? You have to think of them as streets that people live on, that things live on, and that we can use to our advantage, especially in matrices. Okay? Okay, so let's make polygons out of this. So we're making 4-sided polygons, so we want to go to the mesh tab, ribbon, and we want to grab mesh quad, because that is mesh quads are 4-sided. And we're going to plug them in the right order, right? So we were going to start with 1 first. So this is the component that has 1 in it. So that'll go into A. Then we went to 0. So that's this guy. 0 is first there. So we'll plug that into B. Then we're going to go to 3. This component here is the one that has 3 first. So that goes into C. And then 4. And in this case, this component here has 4 first. And then it'll go into D. Okay? That's currently making the instructions for the mesh. So just to sound a bit like a broken record and hone it in, how do you make a mesh? How do you define a mesh? You need a list, a cloud of points, and you need instructions. We've made the instructions. Do we have the points? Yes, they are these guys, these flat points here. So this is our cloud of points. And these are our instructions. So if we look at this, this is made mesh instructions. So quad between 1, 0, 3, and 4, 2, 1, 4, and 5, 4, 3, 6, and 7, etc., etc. So now, if we go and construct a raw mesh, which will be under primitive, construct mesh, if we plug our vertices into that and our flattened faces, that will quite rightly do exactly what this did. Okay, so we've plugged in our points into vertices, our flattened tree into the faces of the flattened mesh quads. And now if I go back and start adding more numbers to this, because our system is written in a way that can handle that, I don't have to worry about, I can make that any number I want. Is that a question? Yeah. Pardon? The points, it's these points here, the ones, these ones generated by the curve intersection that we simplified, trimmed, and then flattened. Okay, so look how much effort it took to make that compared to that, right? Okay, so this isn't necessarily the right way to do it. It's just what's a good example? Give a man a fish, he eats for a day. Teach a man to fish, he'll fish. There's a fish theme today. There's a fish theme. Teach a man to fish, they'll eat for a lifetime, right? So one day you might end up in a position where you do need to do something like this. He's hoping you never have to, but at least you know that if you've got, if you can work out the pattern in your head, then you can get it to work. Now, in my case, I had to do this, not for a square grid, but for an offset hexagonal grid. So that was a nightmare. So that was for a competition that we did for a Chinese stadium. Does anyone support CFFC, China Fortune Football Club? China Fortune Football Club. So you don't know what China Fortune Football Club is? Maybe it has a Chinese name. This club? Does anyone know this club? No one? No, you don't? Okay. Is it funny? Okay, why is that? They're not good? You just don't know them? You know them. So you do know them. They do exist. I'm just trying to be relatable. Just trying to be relatable. Okay, guys, we've made meshes. Fantastic. We've made a mesh. We've made a mesh. Fantastic. But we're not there yet, and we've got an hour and 10 minutes to be there, right? Yes. You can give up one of them. Is it seriously the only 2 PowerPoints in this whole room? There's no other PowerPoints. Okay. Okay, so we've made a mesh. We have achieved the learning aspect of this particular lesson. Now we're going to make something out of it. Okay? So we've got our mesh. We need to, now that we've made it, we are literally going to break it down and get the geometry out of it that we could have got from the previous geometry. Okay? So we're going to grab the face boundary. So what face boundaries is going to do is give us polyline curves that define the boundary of each face. Okay? And we're also going to grab the face normals. So for each of these faces, we're also getting the center point and the normal. Can everyone remember what a normal is? It's certainly someone who is not me. I am not a normal. What? A normal is the vector that is 90 degrees to every point on a surface, right? So if I had a face normal, like my face, then that's the normal, right? Yeah? Or if it's a triangle, it's perpendicular to the surface of the triangle. I'm getting some smiles with my jokes, which is good. Just some smiles. That's all I need. Okay. So the reason that we want the normal is because we're actually going to produce a model of this in 3D of the acrylic that we're going to cut and the various just to work things out. Okay. So when I make this out of acrylic, I don't want the acrylic to touch because there's going to be a frame in the way that's holding the acrylic up. And I need to give the acrylic some space to have the frame, right? So it's at that point that I need to offset the acrylic to make sure that it's not butting against colliding with the frame. So if I have a frame with thickness through here, can anyone suggest really quickly a component, like a function that we could do to these curves to make them avoid the frame, to get smaller to avoid the frame? Offset. Thank you. So we need to offset our curves. We're going to use offset curve purely because I think the other, you could probably use the other one as well. When we offset curves, we need to make sure that they are offsetting on the right plane. In this case, these are all planar, but just to make sure, we're going to produce a plane based on plane normal. We've made planes in the past, but we have never made planes this way because, fortunately, normal. So, how many things have we used in the past to make a plane? Anyone? Like a point, yeah. So if you have a point and two directions, you can make a plane, right? So a point and two vectors. In this case, if you've just got a point and a z vector, you can actually make planes. You just can't control which direction they are pointing, but at least you can control the direction of the face. So that's the cheapest way of making a plane, is with two variables, a location and a z vector. That's it. We're going to use these planes to define the offset, and we are going to set the offset to a variable, and this variable is going to be an important one. Oh geez, I've been scripting into Christina's script. Let's just move that down. So what that'll let us do is define the distance. Now, can anyone see what the issue with this particular distance is? Instead of making the squares smaller, the squares are getting bigger, right? So that number needs to be a negative. So we can do that by, putting an expression in and putting in negative x. Cool. Okay. So then if I want to, right now, this is actually enough geometry, enough information to laser cut acrylic, okay? So you've all done the waffle exercise where we've had 3D geometry, like geometry in 3D that can be placed on a 2D plane and laser cut, yeah? So what components did we use to do that? Orient. We used orient, yeah? And what do you need to orient something? You need a starting plane and a destination plane, right? So, we've all done it on the waffle, therefore I don't need to teach it today. So I'm skipping that, okay? So if you need to laser cut these, you're gonna have to work out how to get them to a flat plane to laser cut them. I'm getting a frustrated face, but the thing is, I've taught it, and now you got to struggle through it. You got to do it again instead of me just hand feeding it to you. Okay? So I've already taught you how to do it. We've done it with the waffle. If anything, it's actually everyone should have components, scripts in the waffle stuff that do this. So just use it. Okay? The key thing is, Blair, if you're annoyed, just listen. I'm going to tell you how to do it, okay? This plane here is the plane that you want to orient from. Remember, you have to generate your own planes of where it's going to orient to, okay? Cool? Okay, we're skipping that bit. Are we cool with that?
Yeah.
Excellent. So, we're going to make a 3D version of this. So it's at this point, the 3D version doesn't necessarily need to be made, apart from like creating renders and whatnot. But we'll just make it so that we've got something to display the glass. Oh shit, that's not right. That's not quite right. Okay, even though I said that, what I just said, it still applies. But there's one other thing that we have to do before we laser cut, okay? And that is, if we were to laser cut this, we're not actually going to produce that shape, yeah? My bad, I forgot to trim, okay? So we just need to trim it before we orient. So, shit, Christina, it's just made it so difficult to get through just one exercise. Okay, so how are we going to do this? How are we going to do this? Okay, so if we have our offset curves and we produce a boundary surface for each one, so what that'll do is we have our flat boundary surfaces, and fortunately it's at this point, if you haven't rotated this properly, these won't work, okay?
Yeah, mine's not rotating.
Okay. So I can help out with that in a bit, but yeah, these won't work at this point, unfortunately. So what we need to do is just get the curve that defines this element. So this guy here, we just need to find the intersection with that and those flat planes to generate a curve to cut them when we laser cut. And shit, okay, now I have to actually teach it because it's now getting more complicated. Okay, that's fine. So what we'll do is we're going to flatten our rotated geometry. For those of you who this isn't working, who has this that it's not working?
Who's working?
No. Okay. In that case, just plug in this component It's called patch. It's going to be a bit slower. Does that work? It's not working?
Yeah, that works.
Okay, it is a bit slower though, right?
A little bit, yeah.
Is that everyone?
Too bad.
Cool. Everyone is aware of that. They're using patch. You're not using patch.
No, I'm still not working.
You're not working.
Yeah.
It's still not working, even though you've patched it.
Because I missed some.
Okay. There's literally no time to.
Yeah.
All I care about right now is you guys understand meshes, which is good. I've taught that bit extensively. Yeah. Now I just need you to get some output, okay? Which is why I'm probably going to ignore everyone's problems and just go full bore, okay? So one other issue is, not issue, if you want to fix, like if you reckon it's just like one slight little issue and we can deal with it with tolerance, then if you go to the curve planar and plug that in, and then we project our offset curves onto that plane, then what we're doing is we're just guaranteeing that they're planar, but they might be a little bit like inaccurate, just a little bit inaccurate, but at least they're planar. So when we plug them into the boundary surface, they'll work. But mine were working anyway. This is why it gets hard with different geometries, because like if you've got something that's completely different to me, then it's going to be hard for me to teach you how to solve it if I don't have it in front of me, and then we could literally go off on a massive tangent just for one student. Okay, so we're just testing for planarity. We're projecting the plane, that geometry onto that plane. Is that now meaning that you can do a boundary surface? Like, try that. I'm pretty sure it would mean that you could do that. Okay, we've got that. Then I want you to go back, get your rotated module, be it rotated or not. We want to project that. So we're going to grab that and bring that all the way to the front. Project it to the ground plane. We're going to offset that. Not offset it, sorry, extrude it, just making it a solid. And the extrusion that we're going to do is going to be basically as high as we can. So this model's roughly this big, right? It's definitely not going to be 2 meters tall. So I'm going to make this 2 meters tall. Done. Okay, so that's giving us geometry that we can then use to create intersections with our boundary surfaces. So we are going to just use a B-rep and B-rep intersection, like so. If I hide everything now that I've done the B-rep intersection, what that should be producing is a series of curves that we can then use to cut our flat panels to match the output. Does that make sense? So, for example, see this panel here? Do you reckon we need to laser cut that?
No.
Cool. See this panel here? Do you reckon we need to laser cut that? Like this panel.
No.
We only need to cut this bit. What we're going to do is we're just going to orient everything. I'm going to let you guys manually remove everything that you don't want to laser cut, so you're not wasting material and I'm not wasting time. Okay? Because like there are ways to do this, but they're defeating the purpose of the exercise. Okay? So fortunately, for each of these, we have a plane here. So if I orient this projected curve Oh, geez. They're going to be all screwed up. Right. So if we set that to graft, our planes to graft, that should all, these guys are all coming into the right location now. Do you remember what we have to do? Do you remember what we have to do to get these to not clump all in the same spot? Yeah, guys. So we just need to create a series of points that effectively. Let's do it because everyone's giving me faces like you asshole. So we're going to create a series. We'll make that at least 500. That's definitely going to be too big. So we're going to change the step size of that. We're going to count the number of planes. So here we go. Under the plane normal, we can get the list length. That'll tell us the number that we need for the series. So that's giving us that. We can use that to generate points that we can use to make planes. And we can use those planes, so if I spread them out, whoop. So we can use these planes to reorient our system, and that just needs to be grafted. What's the deal with like 2 people going at a time?
Always leave for the buddy.
It reminds me of high school when girls went to the toilet. But yeah, what is the deal with 2 people going at a time? Are you guys going to the workshop? What's going on? The workshop. Right. Okay. Okay. So as long as we create this system that is then grafted, so the grafting is important. Because what we're effectively doing is we're just making sure that each panel is within it's like a group of itself, because the curve outputs that we get when we do this B-rep intersection, there could be more than one curve per intersection, right? So that means if we just copy this orient now and use these curves, it should move the curves that you want to trim with into their right location. Okay? I'm getting a look of like, yeah, it's working, but I don't know why it's working. From you. You're like, yeah, and?
No, but I'm just thinking it's going to be so hard to construct an actual model.
Yeah, true.
Because like it's only like it's in a line, and you know.
It's in a line. Yeah, but they're in order.
Yeah, but still.
Okay, well then in that case, this is this is where it gets interesting, because we've got here this number 7 and 5, right? So you could then say, okay, give me a rectangular grid that has 7 and 5, and then if we just pull that over here, and we can define the size of that with this, right? So there's our 7 by 5, yeah? So if we just flatten these points, hopefully, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So we just need the x to be x minus 1. And we need the y to be y minus 1. Oh, sorry, x minus 1 as well. Did that do what we wanted it to do? Yeah, it looks like it. Yeah, that's right. So you can see that one there's the middle one over here. Yeah? And then that one is this one. These are just rotated the wrong way. Right, so that this one is this one, and we can see this guy is this one. It's just that's just the wrong rotation, right? And that's because we used this system where when we created the plane normal, we haven't it's only producing a plane by its normal. It doesn't care which direction the XY is, and that's why they're rotated the wrong way, okay? So just know that, like, when you use cheap systems like that, it can affect you in the future, yeah? So that rotation might be wrong. And I'm going to leave it wrong, okay? Because we've still got shit to do. Cool? It is going to be a hard one to organize because it's both 3D printing and laser cutting in the same model. Okay. The frame.
Unless they're just floating.
Yeah, these guys aren't going to stand up otherwise. So, okay. Hopefully the frame's going to be a lot easier. Okay? We're going to do the frame now. So before we do the frame, just know that if we're going to do a digital image of this, if we create if we use the trim function, this one, the surface split, you can use these curves to split these boundary surfaces, like so, and then it's really up to you to get the edges that you need. Otherwise, this function here is what we use to get the curves to laser cut, but you can also, just for the render, or screenshots and stuff like that of the final thing, if you extrude your acrylic panels digitally, extrude with a amplitude, the amplitude is going to be the normal of the face, and the vector, and the amplitude will be, I'm guessing you guys only have access to 3mm acrylic?
I think so.
Right, well, I have access to 2mm acrylic, but I'm sure it'll be a number between those. So it's at that point that we need to graft, plug that in, and we can see that's now creating like solidified panels, things that actually have mass, and we can use this extruded external shape, the one that we've used to cut with, this guy. We can just use that to create a boolean, and I know I've encouraged you never to use it, but if we do a solid intersection between these two, it should just give us the panels that we need for 3D representation. Now, mind you, this isn't exactly what will be laser cut, because the way you can see the angle at which we're cutting the panel is based on the angle that we cut with that shape, but I think that's fine for the render, like for renders, okay? Like, it doesn't have to be absolutely spot on accurate. Okay, frame. We can do it. We can do the frame. Okay, what type of ways have we generated surfaces currently? We've done extrusions, like solid, so we've done extrusions. What else have we done? Have we lofted?
Yeah, lofted.
We've lofted. We've used 4-point surfaces. Today, we're going to use sweep. I love sweep. Sweep is great. We've used pipe. Do you remember pipe? Do you remember how I said pipe's going to take a lot of effort for the computer? Sweep is kind of like pipe, except it takes less computation and it lets you do things other than circles. Okay? So, what we're going to do is, when we sweep something, we need a rail for the sweep, and we need a shape, okay? So if I put a star at the beginning of that shape as a curve, that's enough. I shouldn't have done something so complex, but that should be enough to generate a sweep of that shape. Do you get it? Okay, cool. So what we can do is, as long as we've got a rail, and we've got rails. You know those polylines that I generated and I said, let's just put these to the side and look at them later? So those polylines are effectively rails. And what we need to do now is define a shape that goes on them, okay? And the shape that we want, the lines that we've generated, if let's say this is the line of the rail, yeah? And we've produced an acrylic panel that does that, and that does that, right? Does that make, like if that's our line, we've got two panels that are like to the left and right of it, right? I'm cutting a section through it, yeah? Like in plan, we're technically looking at that point, yeah? So we've got a line and we've got two panels. So what we want to do is we want to generate a profile around that line, around that as a line as a point that effectively fills the gap between the two of the panels, but then at the same time holds those two panels up. Like so. Okay? So that will then will effectively produce a section for you to drop your panel into. Cool? So we need to draw this profile. Okay? And the key thing is we need to be drawing it around that point. So if my point were here, then if I start drawing this, it's going to be wrong, because the way that our panels are generated are relative to that line, right? The lines were effectively this bottom face of the panel. Does that make sense? So the relevance of where this point is to the profile is super important. Super, super important. Okay? So let's make this profile, and let's make it in the fastest way I can think possible. So it's at this point, I don't want to draw this in space, where I don't want to draw it where where it's going to be, because it's going to be really complicated, right? Where's the easiest place to draw this? On the flat, on 2D, and let's assume that point there, from now on, when we talk about this profile, is 0, 0, 0. Okay? So what we're going to do is we're going to draw this around 0, and it's going to make things so much easier as well when we start using mirror functions, because we can just use the base plane. We can use all of those world XY planes as well. So off to the side, we're going to start a completely new thing. We'll just grab a little XYZ construct point just so that we've got this located. So there it is there. We are going to draw a line from the start point. So from here, I'm going to draw this bigger just so that we've got it. The direction of this line that we're going to draw is up in the Y direction. And the length of it will be, let's say, do we want it to be longer or shorter than our acrylic? Doesn't matter. If the acrylic's going to be 3 mil, then you need to make that a number relevant to 3 mil. So in this case, I'm going to make it the same length as the acrylic. And we can't see it because there's a grid in the way. Okay, so do you remember the number that we offset our acrylic by? This guy? 1, right? So that number is effectively going to help determine how wide we want this little bar to be. Okay? So we're going to grab that value and we're going to use that as a parametric value in this system. Okay, so I'm going to paste that in. So just like you guys, just so you know, you can grab parameters and like slide them around, but if you're moving them from like one really far place to another, it's just worth cutting them, zooming to where you want to go, and pasting in place, which is Control-Shift-P. And that's a lot easier than dragging them around. Okay, so there's our number. So at the moment, we've got a line that's 3 millimeters tall. We've got a number for the offset distance. So if we grab that line and offset it by that distance, that will start to determine the position of this line, right? So then, if I just quickly, Christina's really going to hurt you guys with this one. Hopefully, we'll just use tolerance for to make up for it. So if I've got this line and our offset line, and I plug them both into a loft and flatten, then that will effectively produce a bar that is now representing that. Okay? Cool? We're good?
Yeah.
Okay, we're going to do the exact same thing, but in a different direction now. So we'll just copy these. Oops. But now the direction that we want to go in is X. Done. You good? Everyone good?
Yeah.
Okay, so now all we need to do is turn these lofts into curves. So 2 lofts into curves. I could have done that prior to copying. So now if I hide these two, I just have 2 curves. We want to mirror these 2 curves. And we can do that in the same component. So if I hold shift, that'll mirror them. And then in intersect, under shape, in region, we want region union. If we plug our 2 initial curves and our mirrored curves into the region union, making sure that it's flat, that'll produce a single shape that makes up that profile. And that shape is definitely oriented onto the point that we need it to be oriented to. So there's just one issue here, and that is I've provided our acrylic 1 mil offset, right? And I've made our bar 1 mil in both directions. At the moment, it's like, yeah, it's a tight fit, right? So we probably want to make this a bit smaller than what we're currently making it, okay? So it's at this point here in this offset curve that we could say x times 0.8, which is giving us a 20% tolerance, okay? So you'll see once I hit OK, that's making that a little bit smaller, which is effectively going, okay, we're just going to shave off this point here, just so that, you know, if anything goes wrong, like we've got roughly like half a mil, maybe, safety net, so that we're not, you know, shoving taut acrylic into our 3D printed frame. Okay? I'm looking forward to these 3D models because they're going to look like a mess, I think. Okay, so we've got a profile, we've got a location, and we've got lines. So it's at this point, we want to go back to these guys, these polylines. So I'm just going to put this off to the side. I'll just copy these so that, you know, as if we're working on them. So these are the two polylines from before. And if I just grab one of them, all I need to do is generate a plane on that for us to orient our profile to. So going to curve, under analysis, I can analyze the perpendicular frame at the start of the curve. If I were to pick the start of a curve, what parameter should I be looking at? Yep, 0, but let's make sure that 0 is working by reparametrizing. Okay, so we're going to set the t value to 0. And that'll put planes at the start of each of our curves. Cool. We then, now I think that this might go wrong. I think that it might go wrong, but let's just keep going. And if it does go wrong, we can go back and fix it up. Now that we've got our perp frames where we need them, we just need to orient our profile to those. So using orient, we can take the base plane, which is an XY, the world XY plane. We're going to use that as the source plane. We're going to use our perpendicular frames as our destination, and our region union is the element that is being oriented. So you can see there now we've oriented our curves there. Does anyone see an issue with this? It's going the wrong way. So just to make sure that it's going the right way, what we need to do is take our perpendicular frames and make sure that they are aligned vertically. So if I plug in a unit Z to their align, it'll rotate them. Then what in this profile, what direction would we describe as being up in this relative space? Jamie? So if up is Z in 3D, in 2D, what is up? Yeah. So we want to orient our XY plane to Y. And that goes into the source. So that means we've probably just done, yep. So that means now the Y direction in the 2D space is, we're guaranteeing that that is mapping to the Z direction in 3D. Cool. Is everyone's batteries running out? Is that, yep, okay. So we've got curves, profile curves at the beginning. We've got rails. So they're under surface in sweep. Under freeform, we can find sweep. So if you plug your rail into the R and your profile into the S, that will generate your swept frame.
Why is there sweep 1 and 2?
Because you can sweep, you could sweep something and begin to change its profile at different positions along the curve. So for example, if I swept a circle along a curve to another circle, I could change that circle to be that.
Oh, okay.
And what it's just doing is that second one's allowing you to put in different sized profiles along a sweep.
Yeah.
But this is one we want. Yes?
What goes into R of this week?
The rail. So the rail is effectively the line that was defining the frame. And if I quickly just turn on our 3D elements, you can see they are sitting pretty nicely on our frame. Yeah? Like there's no collision because we've avoided that. As well, this whole geometry is actually convex, so it shouldn't actually have any collision anyway, the way that we're going. right? Cool. So we just need to go in the other direction. So if we just do this exact same process, oops, but with our curves going in the other direction, we begin to generate the full frame. Cool. We're actually, I think we're there. Now, what sweep doesn't do is it doesn't create a solid. It actually leaves the two ends open, okay? If your two ends are open and they are planar, do you think our ends are planar currently? Yes, why? Did the profile that we drew, was that planar? So therefore the ends are right, okay? So we drew a planar profile, therefore the ends will be planar, which means we can quite easily use this element, cap holes. What cap holes does is if you've got any holes in your B-reps that are planar, it'll produce a planar surface to cover them up. Okay, so if I plug these in, and we're working slow, that'll force these to become solids. So if I hide everything, we've got these two frames, and previously we produced this solid guy to do the Boolean intersection with our glazing. Now we can just use that to do it with the frame as well. So we'll copy, or no, we won't copy because it's going to take a bit of time. We're going to use solid intersection with our big fat extrusion. This time we're going to use it with our frame. And so if I hide my elements, apart from what's extruded, we've effectively come up with a framed, did I say framed? We've got a framed, glazed, hyperbolic paraboloid that is laser cuttable and 3D printable. Cool?
Yeah.
Look at that. Now, and I may point out, half of this lesson was just talking about meshes, and it is absolutely unnecessary to use meshes in this, okay? This process does not need meshes, and even if it did, you saw how long it took me to make a mesh using just the components that's given to you. So most of this is about meshes, okay? So just to reiterate, a mesh is a cloud of 3D points with instructions connecting them. Okay? That's all it is. And I hate them. Because every program that most people love in the design environment, especially in architecture, lots of people love SketchUp. Like, you're all doing Arch 1101, and those of you who are architects, what's the most commonly used 3D package, modeling package that architects are using? Right. SketchUp is a mesh modeling package, okay? Everything it makes is a mesh. So everything, like, it doesn't know things are four-sided. It thinks of things as a cloud of points with instructions that connect them, okay? So the processes that we're going through that are using NURBS and using patterns, especially the fact that things are four-sided, It's very difficult to do that with geometry produced by SketchUp. So I think this is important, really caveat to a lot of what we just did. Even though there was a pattern for our square grid, so there's clearly a pattern of 0, 1, 2, 3, 4, 5, 6, 7, 8. There's a clear pattern there, right? There's a nice quadratic topology that we can follow to make this mesh. Yeah? But a lot of your meshes are probably going to look like this when you go to send them to 3D print, right? They end up looking pretty crazy, yeah? Is that, as you're seeing some pretty funky meshes when you go to do STL exports? Yeah? Meshes don't need to have a nice topology. You can make a mesh absolutely fucked up, okay? It can be complete mess. And it's at that point, there is really no pattern in how it's made, okay? And so when you're working with a program that doesn't necessarily care about how something's topographically made and only cares about how it looks as a mesh, then you are going to find that you're going to get outputs like this for things that could literally be described like this, okay? So this is a surface, that circle. How many edges does it have? How many sides does that surface have? Anyone on this side of the broom? Razor blade. Sorry, what's your name again? What? Huh?
Naoki?
Naoki?
Yeah.
You're not Japanese. That's a very Japanese name. Are you Japanese? No. I didn't think you were. Naoki? How many sides does this circle have? Yep, because it's a surface, right? But if I were to make this out of mesh, let's do that now. How many sides does that mesh have? Just have a guess.
130.
Yeah, okay, there's like, there's 50, right? There's 50 sides. We are guaranteed, every time we use a surface, it has 4 sides, right? So that means all the logic that you need to do to work with that in computational design it's always going to be 4 sides. But when you're dealing with a mesh, it could have any number of sides, any number of polygons, any number of seams and edges, right? So meshes are really good for processes where you don't need to necessarily care about the topology. For example, rendering, or solar analysis, or occlusion, or just displaying a geometry. But the instant that we want to start to actually work with it computationally, we want it to be 4-sided. We want it to be NURBS, okay? So if you model a box up in SketchUp, that box is likely going to have 12 sides, not 6, okay? Because it's actually going to be made up of a triangle and 2 triangles per face, yeah? And then you can't actually guarantee which triangle, if this is triangle 0 and this is triangle 1, if we were to explode that as a NURBS B-rep, we'll get all the surfaces, right? The edges, yeah? But if we explode that using a mesh function, it'll explode into that as a surface and that as a surface, okay? So those of you who were in the lecture last week, I made a really important point at the end, which is usually you should be using meshes as a one-way process, okay? You rarely want to use them as a process where you want to pull them back into NURBS environment, okay? And it's exactly that circle that is giving you the reason why you don't want to bring them back. Because if I now take that circle, mesh, and I want to turn that back into a surface, so I go mesh to NURB, look at what is produced. That is a bunch of surfaces, okay? And like I can quickly generate, like I can do a merge all faces, and that might at least like get it all into one object. So you know that I had to do two processes to get it back. But really important thing here is it's not a circle, okay? It's still got the faceted edges, okay? So keep away from meshes as much as you can, okay? Only one way. Only go into a mesh one way. If you ever go in, you're never coming out. Except for this assignment. Yeah? Although, just in case there's anyone here that's dogmatic, that doesn't necessarily have to be true. That's a warning. If you think that you can get in and you can get out, do it. But I've warned you. I've warned you. Shall we leave it? Yeah, we'll finish up. That was a pretty. The pattern things are pretty mind screwy.